In mathematics, specifically in category theory, F-algebras generalize algebraic structure. Rewriting the algebraic laws in terms of morphisms eliminates all references to quantified elements from the axioms, and these algebraic laws may then be glued together in terms of a single functor f, the signature. F-algebras can also be used to represent data structures used in programming, such as lists and trees. The main related concepts are initial F-algebras, which may serve to encapsulate the induction principle, and the dual construction F-algebras. Definition: if C is a category, and C is an endofunctor of C, then an F-algebra is a tuple, where A is an object of C and alpha is a C morphism Fa. The object A is called carrier of the algebra. When it is permissible from context, algebras are often referred to by their carrier only instead of the tuple. A homomorphism from an F-algebra to an F-algebra is a C morphism F, a B such that FO alpha equals beta OF, according to the following diagram. Equipped with these morphisms, F-algebras constitute a category. The dual construction are F-algebras, which are objects A** together with a morphism alpha**, F. Examples: groups. Classically, a group is a set G with a binary operation M, G times GG, or M equals XY, satisfying three axioms: associativity, the existence of an identity element, and the existence of an inverse for each element of the group. Note that the axiom of closure is included in the symbolic definition of M. To treat this in a categorical framework, we first define the identity and inverse as functions C and I respectively. Let C be an arbitrary category with finite products and a terminal object asterisk. The group G is an object in C. The identity function E sends each element in asterisk to 1. The identity element in the group G. The inverse function I sends each element x in G to its inverse x minus 1, satisfying M equals 1. Then a group G can be defined as a four-tuple, which describes a monoid category with only one object G. Each morphism F in this monoid category has an inverse F-1 that satisfies F-1 OF equals FOF -1 equals id. It is then possible to rewrite the axioms in terms of functions xg, yg, zg, m, z equals m, xg, m, x equals m equals x, xg, m, x equals m equals e. Then remove references to the elements of G. M equals m, m equals m equals id, m equals e, which is the same as claiming commutativity for the following diagrams. Now use the coat product to glue the three morphisms in one. Alpha equals E plus I plus M. According to this defines a group as a F-algebra where F is the functor F equals 1 plus G times G. Note 1. The above construction is used to define group objects over an arbitrary category with finite products and a terminal object asterisk. When the category admits finite coproducts, the group objects are F-algebra. For example, finite groups are F-algebras in the category of finite sets and Lie groups are F-algebras in the category of smooth manifolds with smooth maps. Algebraic structures. Going one step ahead of universal algebra, most algebraic structures are F-algebras. For example, abelian groups are F-algebras for the same functor F equals 1 plus GXG as for groups with an additional axiom for commutativity. MT equals M, where T equals is the transpose on GXG. Monoids, which generalize groups in that a monoid element does not need to have an inverse, are F-algebras of signature F equals 1 plus MXM. In the same vein, semigroups are F-algebras of signature F equals SXS rings. Domains and fields are also F-algebras with a signature involving two laws plus RxRR, an additive identity 0 to 1R, a multiplicative identity 1 to 1R, and an additive inverse for each element, RR. As all these functions share the same codomain R, they can be glued into a single signature function 1 plus R plus RxR plus RxRR, with axioms to express associativity, distributivity. This makes rings F-algebras on the category of sets with signature 1 plus R plus RxR plus RxR. Alternatively, we can look at the functor F equals 1 plus RxR in the category of groups. In that context, the multiplication is a homomorphism, meaning M equals M plus M and M equals M plus M, which are precisely the distributivity conditions. Therefore, rings are F-algebras of signature 1 plus RxR over the category of groups, which satisfies two axioms. When we come to vector spaces and modules, the signature functor includes a scalar multiplication kxe, and the signature F equals 1 plus E plus kxe is parametrized by K over the category of fields, or rings. Algebras can be viewed as F-algebras of signature 1 plus A plus AXA plus kxe over the category of sets, of signature 1 plus AXA over the category of modules, and of signature kxe over the category of rings. Lattice. Not all mathematical structures are F-algebras. For example, a poset P may be defined in categorical terms with a morphism S, P omega, on a subobject classifier equals 1 precisely when x, y. The axioms restricting the morphism S to define a poset can be rewritten in terms of morphisms. However, as the codomain of S is omega and not P, it is not an F-algebra. However, lattices in which every two elements have a supremum and an infimum, and in particular total orders in which every two elements are comparable, are F-algebras. This is because they can equivalently be defined in terms of the algebraic operations xy equals inf and xy equals subject to certain axioms. Thus they are F-algebras of signature pxp plus pxp. It is often said that lattice theory draws on both order theory and universal algebra. Recurrence. Consider the functor that sends a set to. Here, set denotes the category of sets, denotes the usual coproduct given by disjoint union, and 1 is a terminal object. Then the set of natural numbers together with the function, which is the coproduct of the functions and is an algebra. Initial F-algebra. If the category of F-algebras for a given endofunctor F has an initial object, it is called an initial algebra. The algebra in the above example is an initial algebra. Various finite data structures used in programming, such as lists and trees, can be obtained as initial algebras of specific endofunctors. Types defined by using least fixed point construct with functor F can be regarded as an initial F-algebra, provided that parametricity holds for the type. See also universal algebra, terminal F-algebra. In a dual way, similar relationship exists between notions of greatest fixed point in terminal F-algebra. These can be used for allowing potentially infinite objects while maintaining strong normalization property. In the strongly normalizing charity programming language, co-inductive data types can be used achieving surprising results, e.g., defining lookup constructs to implement such strong functions like the Ackermann function.